In this chapter, we briefly look into system dynamics. In urban planning, we usually deal with models that include changes over time. The temporal change is the dynamic aspect of a system. Therefore, we call these models or this domain system dynamics. As example, let us consider the urban system as formulated by Richard Rogers in his book Cities for a Small Planet, in which he investigates the conditions for more sustainable future cities. Here, the concept of urban metabolism plays a key role. Ideally, we can reduce the inputs and outputs of the system of a city and develop a recycling model, a recycling system for its resources saving supply. So as you can see in the diagram behind me, the bold lines, the bold arrows, they represent the recycle loops, the recycle system, and we try to minimize the inputs and the outputs that we need for a city. This means it becomes more and more sustainable if it's somehow self-sustaining. In a general definition, urban metabolism is a model to facilitate the description and analysis of the flows of the materials and energy within cities, such as undertaken in a material flow analysis of a city. It provides researchers with a metaphorical framework to study the interactions of natural and human systems in specific regions. This definition is already a very nice basis for our future computational models that we will develop also in the next modules. Since we aim to plan more sustainable future cities with our computational planning methods, let's consider the idea of sustainability for a moment. The only option that we have for a functioning future world is not exceeding the regenerative capacity of the system. The system, of course, is our planet Earth. So the first domain, the first area that has discovered somehow sustainability is forestry, where you can harvest wood, but at the same time you need to plant new trees that have to grow for 50 or 100 years. So you have to think ahead how to maintain the cycle of a sustainable forest system that you and your children can use for the production of wood, for building houses, ships, and so on. If you don't do it in a sustainable way, you will somehow harvest all the trees, and then you will have a country without trees, and you cannot build anymore anything out of wood. Sustainability has three main domains. Environmentally sustainable no longer only implies using natural resources at a rate not exceeding their regenerative capacity. It nowadays also implies minimizing emissions of pollutants to the air, water, and soil. Economic sustainability implies balancing costs and revenues so that the system can sustain over a longer time. Social sustainability ensures that production systems such as a farm are socially accepted and that the people living in a city have very good relationships to each others and or that they are supplied with central functions so that there is a fair distribution of public goods in a city and a region. Unfortunately, today we are far away from not exceeding the regenerative capacity of the system. As mentioned, the system is our planet Earth, and we only have one starship Earth, as Buckminster Fuller described it. So we are traveling on our planet, on our starship Earth, through the universe, through space, and we depend on having a sustainable system that ensures that we maintain well our planet. Nowadays we are living in death at the expenses of future generations. We don't run the starship in a sustainable way. If we build the global environment in the ecological standard of Germany, we would need 2.6 Earths or starships to maintain this development, as you can see it in this diagram behind me. If we build the ecological standards of the current world in average, we will need 1.4 Earths, which is still too much. And that it is that low compared to the German standards is that the developed countries have a lower living standard. They don't consume that much resources as we. So thanks to them, we have on average a better footprint. But it's clear that we in the developed countries, we need to reduce our resources. We need to change the way how we consume the resources of the earth, and we need to change our lifestyle. Sounds relatively simple, but it is not. You can make a test of the consumption level of yourself. You may think you don't need a lot, but if you go to this website footprintnetwork.org, they will ask you a few questions, and you will see how much you consume, what's the level of earths that you and your personal lifestyle needs. Next, we should briefly look into the formal notation of dynamic system models. There are different graphical elements for representing various elements or behaviors between these elements. We come to this notation system later when we implement our first own model in the following modules. For your own study, you could have a first look at the references that explains the modeling of these dynamic systems. There are very useful tools for implementing dynamic simulations. A nice and playful tool is Loopy, which helps to understand the basic ideas of dynamic simulations as explained in this module so far. Loopy illustrates well effects of oscillators and feedback loops, why it's called Loopy. So you can link oscillators and observe how they changes iteratively the behavior of a system. But we cannot represent space explicitly with this tool. Therefore, there's another one called NetLogo that offers the representation of space as a layer of cells in a grid that can store all kinds of information and interact with mobile agents which move across the cell space. So the agents and the cells can exchange information. So the cells' states can change based on this information, and the agents make some decisions based on the information they collect from this simple environment. This setup is the basis for so-called agent-based simulations. NetLogo offers as well a fantastic collection of scientific models from many domains, as you can see in this library behind me. Just download NetLogo and explore the models, because they give you really a great insight to problems, to models from other domains, where scientists try to explain the solutions of problems or try to explain phenomena by implementing a simulation and grow the simulation, grow the explanation, so to say, by applying the simulation. Because sometimes you cannot explain things in a static way. You really need to run a simulation showing that the rules that you have implemented recreates certain patterns or phenomena that you aim to explain. Probably the best known and one of the first dynamic urban models is the one represented by J. Forrester from 1969. It aims to simulate all important aspects of an urban system to predict its future development and to better understand the effects of planning interventions. Based on this model, we have nowadays comprehensive urban simulation models. Besides the scientific interests of the modelers, these models are made for policy and planning consultations. Whereas there are some major critics of these models. First, it's very difficult, if not impossible, to provide all the necessary data that is needed for the inputs to start the model. Furthermore, it's difficult to understand the impacts of missing or wrong data sets or data with different timestamps on the result of the model. Because of the second main critic, the models itself are so complicated and the complex interactions of their parts results in a kind of black box model, which means that their behavior is very difficult to understand and there is no clear cause and effect relationship between the inputs and the outputs of the model. To avoid this overcomplicatedness of urban models, we concentrate on smaller, more specific aspects in our investigations in the following modules. Nevertheless, the large-scale urban models are very fascinating, as we exemplify by Forrester's urban dynamics model that is implemented by the simulation framework AnyLogic, as it's shown in this animation. So this model includes some basic mechanisms how attractive certain locations are, for example, for the location choice of firms to create new jobs, and these new jobs attract people to come to the city or to move closer to these jobs. But at the same time, they also cause travel or they cause trips, and you can measure the travel of the total or the total travel in the system that causes or that creates some pollutions, and now you can try to reduce the pollution by other transport modes or by somehow mixing the land uses in a different way and testing policies based on your model. Of course, you have to remember that this model also, if it looks nice and very realistic, it's only a model with very basic mechanisms that fulfill certain purposes. They are not 100% realistic. This is not the one-to-one representation of reality. It just concentrates on certain aspects, like the links of the population growth with some economic conditions in a city, the employment rate and other things that you can see in the simulation here.